We have a new speaker to DConf here. First time. Artha is going to talk to us about exploring declarative capabilities of D. So, by all means, go for it.
Hi, I'm Artha, and I'm very glad to be here. Thank you. I'm very excited, and I'm really itching to tell you about this. Like it has been announced, I'm going to talk about declarative programming. So for some context, I'm the author of Fluid. Some of you might have heard about it. Well, it's a user interface library, which is obviously declarative. What I want to point out today is what makes D great for declarative programming. After all, it's my choice language. Out of so many possibilities, so many available languages, I chose D, and I made Fluid with it. So I want to show you how it's good for declarative programming using metaprogramming, and how can you take advantage of it. So when I say user interfaces, I mean means of communication, right? I'm a human. Here I've got my computer, which doesn't really want to talk with me. We don't speak the same language, right? And yet the computer has a task, has a job, and I need to control what it's doing. I need to somehow talk to it, somehow communicate with it. And this is the job of user interfaces. Despite us not having a common language, not being able to talk to it, user interfaces make this communication possible. In context of Fluid, we'll be talking about graphical user interfaces. So we have a surface, a screen that we will present data, information on. And now, using the same screen, presenting components, interactive components, we're going to use a mouse or a keyboard to talk to the computer. So a user interface will consist of components that will reappear all this time. Like if we have something, the user, for example, has a confirm an action, like in the slide previously, we are going to have buttons. Every button is going to act alike. They have differences in size, text, and styling, but more or less they're going to have the same job. I'm just going to assign a different function that is going to perform when clicked, but it's going to be a button no matter what it does. We've got a lot of other components. So for example, if I want the user to type the name with a text box, that's the component I want to use. But it's not just components, right? Say I have a screen. The screen has limited space, and I need to assign these components, place them, lay them out on the screen in a way that makes it readable, clean, intuitive. Consider how many variables we have here. The text can have varying size. We can have long text, short text. We can have images of different proportions. Now, I said we have user input, right? So we have data that is going to change. So you might have more or less components, more or less information, different quantities of everything. Add to this, in this age, we also have all sizes of screens, from mobile phones that are so tiny, laptops, and screens as big as this one. Now, also different proportions. This is a landscape screen. This might be a portrait screen. So we also have to take this into account. We call this responsive user interface. We also have to consider that users have different needs in terms of accessibility. So for example, if I have some small text on the user interface I've designed, then maybe it might not be readable to everyone. So for example, they might want to set a minimum text size that we can't cross. It will be enforced. And a user interface needs to adapt to this requirement. So a user interface designer will have the job of creating a user interface, and maybe they will make a sketch of a user interface that looks like this. To present this, after all, the computer has to understand this just as well. We might prepare a sketch on paper, but now the computer needs to understand our user interface, so we can actually display it on a screen and then make it interactive. So for example, maybe I'd like some text up here. Pretend this is text, all right? Underneath some more text, smaller, yeah, nice. Now, I need some dynamic content, right? So maybe some text on the right next to this little one, not the one at the top, with some buttons, oh, like this. See, you probably recognize this already. This is a tree. User interfaces may be made with a tree. There are different ways, of course. It doesn't have to be a tree. But As far as I know, this is the most common way, and Fluid also does user interfaces with a tree. So this is what we're going with. User interface designer prepared the sketch that we have seen just a while ago. Now their job is done, and they pass it to a programmer. And our programmer wrote this code. Oh. This is gross. Look, I just told you, this is supposed to be a tree. This is not a tree at all. This is completely flat. Maybe if I look at this, I can see after a moment that this is a user interface because there are some common keywords. If I want to see what this is actually doing, I will definitely need a piece of paper, sketch it down, see what it is actually doing, but I can't read this code just seeing it. It's not enough. If you want to make it look like a tree, then maybe we could use a different format. XML is pretty common. Probably seen something like this before. So now we have this. We turn it into this, an XML file. This is much nicer. This is a tree. It's clear. Every tag in XML represents a component, and attributes let us design, specify all the properties that define the layout and values the content. This is nice, but now we have to make this interactive, right? So I have pressed onClick right here, but what is onClick? I never defined what onClick is, so now I need to bind it into decode now. We get something like this. For example, it doesn't have to look like this, but in this case, we need to know that the identifier I have here in XML is actually this delegate here. We need to bind it together. All right, what about dynamic content? This frame, maybe I need to add more labels, add more text or different components, depending on the information that we have, depending on what the user actually has provided. So our next step is this. We create an attribute called ID, and now given this ID, we can insert new items into this frame. Things are getting pretty ugly here already. See, I have an array of items, and I need to load another XML file, or if I want to take a shortcut, I could create a new label or whatever component I need on the spot, but if you want to stay idiomatic, we are going to have to load another XML file. We need to find whatever content we have in there, and we need to update the text. We need to add the element then, and things are getting pretty nasty at this point already. Maybe we could, someone has this clever idea that we could use templates, right? Inside this XML file, we add those pretty tags that say for every item in this list on the left, we will create a new label and fill it with the text in the list. Cool, right? Not really, not really. See, templates are so complex when you look at this. It just takes a while to see that we already have 3 languages involved. We have D, we have XML, and now we have another template language. And furthermore, 2 of these languages are programming languages, which means that we have 2 distinct programming languages with different semantics. Every once in a while, this is going to bite us because we forget, for example, that something doesn't work like this in one language, something works differently in the other language. Also, because this is an XML file that will probably run at runtime. We'll probably load it at runtime. Of course, there are things like diet, but I'm not going to cover that. Usually, these things will be runtime, right? So now we have to bundle a runtime for this language, for this template language, along with an app in order to actually fill what this template here does to make it work. And those runtimes usually aren't cheap, and this is a lot of overhead going on in here. We could do it better, right? I hope we do. Let's think about this for a moment. Does anyone write arrays like this? There are some use cases, right? But usually there's no need. We can do something like this, right? We have a nice array literal, it does the job. Couldn't we apply something like this to our user interface? Couldn't we make our components this way? So I'm here to present you how Fluid does it. This is nicely, immediately you can see this is a tree. We can immediately see we have components, vframe label, hframe label, vframe label button. Additionally, with all the properties like the layout that we have specified earlier in XML, and we also need no binding because D handled this. D has a full namespacing, module system, everything. We can add all the dynamic content inline using names from D, and I can also specify the delegate I wanted right in the code. Neat. So if we want to make a user interface like this, where do we start? Let's see. A user interface has multiple layers that we need to go through. When I make a window, the first thing, I'll need some context, right? Content. I have to display some text, information, wherever. That's one thing. Second thing is layout. I need to place all the things on the screen. And thirdly, I need to style them. Need to, like I said, my buttons might need to look differently depending on whatever the designer required me to do. So let's start with content. Fluid is object-oriented underneath the declarative layer. So maybe for constructors, let's go simple and just go with content. A label is there to display text. So a label is going to take a string of text in order to have something to display. A button actually is a label underneath. There are different types of buttons. We can have a button that displays some text that we can press. We could have a confirmation button that says OK, so we can confirm our action, press OK, we're done. And furthermore, a button needs to do something whenever it is pressed, so we also bind the delegate on the spec. Simple enough. An image view is there to display pictures. A path to an image is going to do the job. Maybe if I want to, I can also pass image data on the spot. We could use more components to create our user interface with more components. So a frame is another component that is going to display our things, just like in the example I showed earlier with the tree. A frame, in case of Fluid, actually does the job of a column or a row. Now that we have all those components and we know that their constructors are going to take content, there's just a little thing I need to complain about, is that our frame could fill two roles. It could either align the components it contains in a column vertically or in a row horizontally. Now we have a single constructor because as I said earlier, we have a rule of thumb. Our constructor will only take in content. So our frame, how do we say if it's vertical or horizontal? We could use a static method. So one static method will create a frame and make it vertical. One static method will create a frame that is horizontal. We will have a button, and a button uses a regular constructor because there's just one main text button. Other types of buttons will be a different type of component. Like a frame button will actually be a frame that acts like a button. So we have a frame button with two static methods, and now we have a number input, which is a template, and you probably see where this is going. This is inconsistent. Like, I don't want to remember whenever I have to use a dot in a name or when I have to type new and when I don't. So maybe we could simplify this a bit with the most powerful primitive that D offers us. It's called a function. We could use a vframe function and an hframe function to specify if our frame is going to be vertical or horizontal. Similarly, we can create a button with a button function, a vframe button for a vertical frame button, an hframe button for a horizontal button, and so on. We can also make shortcuts for templates that we instantiate very often, like int input, float input. Now, we've covered content. So how about layout? See, I've said we have frames. In this case, we have two horizontal frames, each with 3 nodes inside, except for the text. This, we have 3 tightly squeezed components very close to each other that have a lot of remaining space. And below, we have 3 components that occupy all of the space that we have here. We need to set a distinction because a frame itself does not specify which one of these 2 it will be. We have 2 special properties that every node can specify. We call them expand and align. In case of Fluid, some frameworks do it differently. A node that expands, that has expand set to 1 or more, will take all the remaining space, or rather a fraction of the remaining space that no node needs as a requirement, as a minimum. So in this case, for example, we have in the second row, we have 3 components with expand1 that each take a fraction of the space that is available. This way, we have 3 columns equally sized. Here, next to these 2 components, we have one frame that has expand set to 1 and align set to fill. The alignment makes it so, unlike the components on the bottom that take up space but don't actually use it, align fill makes the component use the space it has expanded to. So these components on the bottom instead have different align values, align left, align center, align right, which places them relative to the box that they have been assigned, the space that they have expanded to. It defines how they're placed within the space they occupy, simply. Now, to do this with frame, we're going to use the previously mentioned tags, like these ones. A layout template function takes a number and a string. The number defines our expand property. The string defines the alignment property. For what it's worth, expand is a number and not a Boolean, because you can make a component take 2 columns instead of just 1 if you need more control over the space. But most often it's just 1. We can stack as many of these as we want, so I can put a frame and I can set a theme which checks another box that we've prepared. We have styling now. All the 3 layers are now complete. On top of that, we have a layout, and we also have other tags, like tags. Actually, a misnomer. I should have called it properties from the start. It's called node properties. But I could use a tags property to specify the tags for a node, which allow for organization. That is very similar to CSS classes. For example, I don't want a component to be visible from the start. Maybe I want to prepare it for later use. So I can use a hidden property to hide it and show it later. A disabled property is for nodes that I don't want the user to interact with yet. Maybe they're anxious and they're not ready yet. And maybe for other components, we could also define other properties, like a frame. Maybe we want to support drag and drop, so I want to be able to drag one component and drop into the frame we have prepared here. Accept drop does the job. A size limit is for size-locked nodes and allows me to restrict the size that the node will take. This is very helpful for responsive layouts. What I call this is the node builder. This is the node builder pattern, similarly to the builder pattern that you might find often in object-oriented programming languages like Java, which in this case, we create a node, and the second thing we do is we set the properties on the node using the builder pattern. So in this case, the function that creates the frame is what we call the node builder, and these parameters, these properties, these purple fields, parameters, we call them node parameters. This is terminology specific to Fluid. It does not apply to other frameworks, but I just want to make that clear because I will use these in the rest of the presentation. We can create our own node properties by creating a struct with an apply function, an apply method. This method has to take a node. Properties don't have to apply to every node. Maybe I want them to only work on a frame or on a size-locked node. So I can replace the node parameter here with another type of node. And it will only apply to these types of nodes that I want it to work on. Inside, I define what exactly this property is going to do. So for example, the hidden property on the left is going to do exactly what it does on the right. This is actually the actual definition in Fluid source code. It just says the isHidden property to true. Properties are usually simple. They don't do anything too complex. Instead, usually they just control behavior that is defined within the node itself. What we have on the left is really more or less equivalent to what we have on the right. I've also mentioned variants, like we could have a horizontal or vertical frame. To make that behavior work, our H frame is going to differ from a VFrame function by setting a node is horizontal property to true the moment the node is created. You might ask, what makes this different from UFCS? Because these are very similar. So isn't this just UFCS with extra steps? More simple example is that in case of a component, these properties are usually, there's very few of them. The ratio of properties to content is usually very small. So when I see a node, it is really far more comfortable for me to have them at the very top of the node, because this just makes my job easier when reading the code. I can immediately see what's going on. For example, by seeing the theme that is applied, I can immediately know that this node has a certain styling properties or whatever. Content is slightly less important. And also it does make some decorational visual changes, like in case of UFCS, I do think that in a tree structure, UFCS is a bit awkward to use. Like, this formatting is weird. So in case of a node builder, we instead place them inside the parentheses, which makes it very clear that these properties apply to the node that we are creating, and this is like obvious, I hope. I don't say that UFCS is bad. I actually love UFCS, but I think UFCS is better for properties that are transformative, like, for example, mathematical transformation, geometrical transformation are a perfect example of using UFCS, or ranges. In this case, we are creating a node immediately with some properties set, so a node builder, in my opinion, is just more appropriate for the use case. Oh, something went wrong with the PDF. I did not see that. So it's time for the magician to reveal the magic. A node builder inside Fluid is made with a template. This is a node builder template, which takes a parameter that defines which component the node builder is going to build. So a VFrame node builder is going to build a frame. In case we have a variant like an H-frame, we can set the property like I showed you earlier through a delegate that will set it immediately the moment the node is created. Like the misplaced node is supposed to show you, I should really note that I've very recently coined the term node builder. So inside of Fluid, for the lack of better name, it was always called simple constructor, and it remains so in the source code. Only the very latest version that I've released like less than a week before DConf, node builder is even available at all. So you'll still see simple constructor all over the place if you use Fluid. Just saying. Now strap in, because I'm going to show you some metaprogramming. And as simple as it is for metaprogramming sense, I do still think it can get pretty difficult to understand at times. So what a node builder is I've lied to you because I said it's a function, it's actually a struct. There's a few things that make it easier for later metaprogramming use, that make it more practical to use a struct over a function, but whatever, it doesn't matter, it could be a function if I wanted it to. Now, we created the struct by passing the frame parameter into the struct. The struct is templated just as well. So the node builder is also going to take the same parameters that the template above takes. And from now on, inside the node builder, we will refer to the type that we are creating using the magical keyword type. So whenever you see type from now on inside the struct, you know we mean a frame. Now, to make our node builder behave like a function, we need to overload the opcall function. You can check the spec, it's in operator overloading. Opcall lets us define what happens if we try to call the struct as if it was a function. It returns a type, like I mentioned earlier, which means it returns the frame. And it takes a variable template parameter args, which lets us take as many arguments as are needed. The user, while calling this function, can pass it as many parameters from 0 to 100 or more, however unpractical that might be. And what this lets us do as the programmer, as the developers of this function, it lets us check the type, analyze the type of each argument, which is going to come really handy in the next step, as we have to split the parameters, the node parameters from the content that we are going to pass into the constructor of the function. We have to draw a line between them. So the first thing we're going to do is to calculate the number of parameters that we have. In a case like this, where we have two labels inside a frame and no parameters, the parameter count is going to be 0. In a case like this, when you have two parameters and two labels inside, the parameter count is going to be 2 because we have two properties at the top. Edge case, however, we are not going to accept cases where the parameter will be somewhere after the content, mixed with the content. We want them to be at the top because otherwise we are just missing the point. Besides, it also makes things simpler. So on leading parameters function will return parameter count 1 in this scenario. Leading parameter is rather straightforward. We're going to iterate on each of the parameters earlier, on the types, and we're going to go through each type and return the index of the first type that is not a node parameter. In case we have a function that is full of node parameters, that means the argument count is the exact same as the count of parameters, and that's the whole function we have. For example, if you have a call like this, a theme is a node parameter, all right. Layout is a node parameter, all right. Label is not a node parameter, and its index is 2, so we are going to return 2, which matches a parameter count 2. To check if a type is actually a node parameter, we are going to use traits compiles simply to see if this call to apply will compile. There's nothing complex about this one. They don't need to work on the init values themselves. They most likely won't. But the point is that these have to compile. All we're checking is if this parameter, if this type is actually compatible with the node, and also if it actually has an apply method that could work, right? So, for example, a theme will work on a V-frame because it has an apply method. A layout will work on a V-frame because it has an apply method that accepts a V-frame. However, a label method does not have an apply function at all, let alone one that would work with V-frame, so it is not a node parameter. And size limit, however, like I said earlier, will only work on a size-locked node, not on a regular V-frame, so it also won't work. This will be rejected at compile time. Now, to finish our job, we are going to pass all the parameters after the line that define our content and pass them into the constructor. The remaining parameters, the ones before the line, are going to be our node parameters, so we are going to call the apply method on the resulting node. And also, in case we have a variant like HFrame, we are going to call the function that we've passed into the second parameter, if this was 1, in order to make sure it creates the right variant. Like in this case, a direction horizontal for a horizontal frame. And that really is it. As a side note, actually, because I did not make a slide for it, you might also ask me why didn't I use named arguments? The answer is as simple as the time as I created Fluid, there was no named arguments. But it's also, if you recall the argument as the slide when I said why not UFCS, named arguments also fail there, because usually they will be placed after the content, not before, but also they're still beta quality, so they don't work well with templates or inheritance. So thank you very much for listening in. If you want to try Fluid out, then there's dub init tfluid will do the job, but just please make sure to use the latest version because dub doesn't always fetch the latest. I don't know how it works. In case you feel so inclined, you can also sponsor me on Patreon to help Fluid's development. Thank you very much. Time for questions.
I want to, first of all, thank you for your nice presentation. And last night at DConf, I was already talking with Attila about how GUI programming sucks and all the libraries are awful. So I'm always nice to see some actually, nicer interfaces for that. So as a question, first of all, have you heard of immediate mode GUIs?
Yes, I did.
So the question then is, have you considered using that, and why did you choose this approach?
It was a while ago when I decided that Fluid would be a stateful framework. And I think the reason is I'm just a lot more familiar with how stateful ones work in general. I have a lot of familiarity with it because I've worked with so many stateful ones before, and at the time I started creating Fluid, I actually did not use an immediate mode library, not even once.
When it comes to writing these modules and having like the layout, the content and whatnot, as well as like the styling information, like whether there's spacing in between, the font size, these kinds of things, what are your thoughts about systems that completely separate like the style from the contents, kind of like CSS and HTML? And I recently read that GTK apparently can load certain CSS properties, which I was surprised to learn. What are your thoughts about a complete separation of style and content?
Well, if by complete CSS is enough, then I actually really like it. I really like it, but in case of CSS, I don't like it exactly because CSS is not, CSS also does layout actually, because you specify display type inside of CSS. But other than that, I'm a big supporter of separating styling from the content myself. And Fluid also does that. What I showed you here is that you have a node parameter for theme, which lets you like I said, connect it with the actual theme set earlier, defined earlier in like a style sheet. And you also have tags, which, like I said, are basically the equivalent of CSS classes. For what it's worth, I did not show you because I thought I wouldn't have the time for it. Fluid actually also has a declarative API for creating themes just as well. But it's a bit more quirky than this one, actually.
We have a question from Ricky on YouTube. Would you consider swapping those strings for alignment to the memberof operator? Yeah,
actually, I would. I originally used strings exactly because we did not have a memberof operator. So if in case we do get one added, it would be very, very nice.
Is there any more questions out there? Going once? Going twice? 2.5? All right, we're done. Thank you.
Thank you.